Hi guys, welcome to, I mistitled that, your chapter 20 video. And what we're going to work with today, the nice thing about this is that there's no true new math here. Everything that we're doing is actually going back to building off of, rather, chapter 18 ideas where we were given for instance, a population proportion, and we wanted to make conclusions about how samples behaved based upon that population proportion. So that's the essential math that we have here. Looking back at what we've seen in chapters 18 and 19 so far, and then I will recap on what we've seen in 18, 19, and 20 when this video is done. In 18, we talked about how the conclusions that we can make for sample means if we have a population mean, and we talked about the conclusions we can make for sample proportions if we have a population proportion. Remember that one of the keys to look for when you're solving a problem that involves either questions about samples of means or proportions, pay attention to the type of data that you've got to work with. If you have the data you care to know about is like preferences that people have, or favorite colors, also falling into preferences, or sex, or major in school, all of that is a great question to answer with information or with a proportion, because that's not numerical data, that's quantitative, or that's categorical. If you've got numerical data, quantitative data, then that's the sort of question where you're going to be working with, excuse me, you're going to be working with more sample means. And so that's something to pay attention to. What's the underlying data look like? In this chapter, we're going to start to do hypothesis testing. I think it's kind of cool. I know it's going to seem a little weird at first, as much of this unit has. You guys have done a lot of hard work for me so far. Pay good attention to this, and come to me with questions next time I see you. Okay, so that was 18. I guess I should have said. And then 19, we've talked about confidence intervals, and we talked about those recently, so I'm not going to reiterate those. Now, before I go forward with chapter 20, I want you to think in terms of how the court of law works. And that seems a little weird, I know, but that's actually, that analogy is going to stick with almost everything we do in chapter 20. When in the court of law, someone is on trial, we do not automatically assume that they are guilty and then try to prove that they are innocent. Instead, we assume the baseline assumption is that they are innocent, and then we build up evidence to determine whether or not we can conclude reasonably that they are guilty. Now, unfortunately, we don't conclude beyond a shadow of a doubt, and that's going to work the same way in chapter 20. We're going to make a baseline assumption that the defendant is innocent, and we're going to build up information trying to conclude that they are guilty. Now, if we cannot conclude they are guilty, we don't say that they are innocent. We just can say that we can conclude that they are not guilty. Same way here when we work with hypothesis testing. That'll make more sense here in just a second. All right, let's get started. I've got two examples for you guys. If there were no home field advantage, the home teams would win about half of all games played. In the 2003 Major League Baseball season, there were 2,429 regular season games. It turns out that the home team won 1,335 of these 2,429 games, or 54.96% of the time the home team won. Could this deviation from 50% be explained just from natural sampling variability, or is this evidence to suggest that there really is a home field advantage, at least in professional baseball? Okay, so we want to test to see whether or not this population proportion that we would expect that you would win 50% of the time, regardless of whether or not you have the home field advantage, is true. It is the defendant on trial here. So we're going to set up two hypotheses. They are as follows. The first, we will call that capital H naught. That is the null hypothesis. That's our baseline assumption. That's what the defendant is claiming to be. The null hypothesis is that the true population proportion of games won is 50%, i.e. home field advantage is not a thing. Now the alternative hypothesis, and the alternative is the thing we're building up information to support, that would be that the true population proportion for teams playing at home would be greater than 0.50. And that's what we want to analyze. Now, okay, now to a model. I said that we were going to use Chapter 18 ideas. So we're actually going to work with, if we know that P is equal to 0.50, we want to look at this sample here that has the 2,429 games. We're going to use the normal bell curve for a distribution of sample proportions. So all these conditions that we've checked in the past still hold. So for the model piece here, we're going to check randomization. So do these 2,429 games represent a fair random sampling of all the games played in Major League sports? So we have to assume that. We don't really know that because they're all coming from the same year, I think 2003. Yeah. Okay, so we're going to say, we're assuming, and that's the best we can do, the 2,429 2003 games, from the year 2003 that is, represent a random sample. Of all pro games, or really, yeah, we're looking at pro games here specifically. That's our population. Okay, so randomization condition, maybe not met, but we explained how we're assuming that, and it doesn't seem unreasonable to assume. 10% condition is met here because 2,429 games from the year 2003 is certainly less than 10% of all games played. All, I should really qualify that with professional games played. Pro games played. All right, we're doing fine. So there's the 10% condition met, no sweat. Let's look at finally the success failure condition. So that's the NP and the NQ. Are they greater than 10? We're going to change how we write that just a tad. The sample size times, instead of P, we'll say P naught. So the population proportion given our null hypothesis, the capital H naught hypothesis, that's what the defendant's claiming to be. Remember that. NP naught here was 0.50. N equal to, it was 2,429 games. So 2,429 substituted for N times the 50, that's certainly greater than 10. So we'll check that off. And then failure would be NQ naught. Again, the naught's just referring to the baseline assumption, what the defendant is claiming to be 2,429 times the same 0.50, also clearly greater than 10. So those conditions have been met. All right, now for our model. This is a slight deviation from what we would have done in 18. We didn't mention what model we were using in our null hypothesis in this courtroom case. We need to mention the courtroom what the model we're using is. And throughout this entire chapter, it's the same one in chapter 20. So that's kind of nice. If you can remember this, you'll be good throughout the whole chapter. It is the one proportion z-test. And it's got a fancy name, but again, the bell curve's no different than what we've seen in the past. So we're going to build this bell curve here, and we're going to use it to look at how deviant these 1,335 of the 2,429 games was from our baseline 50% win rate assumption for home teams. So, line, oh, getting a phone call. I'll ignore that. So what do we need here? Well, let's go ahead and label the bell curve. This is a, it's in blue, just so it catches your eye, distribution of sample proportions, like that, and the expected value of p hat, the expected value of any particular sample, given our null hypothesis assumption, what the defendant is claiming to be is 0.50. The standard deviation of a sample proportion, because we are, notice we're working with p here, not p hat. So it is standard deviation, not standard error. Standard deviation of p hat is equal to square root of, we'll write p naught q naught over n. Proportion of success under the null hypothesis, proportion of failure under the null hypothesis, all over the sample size, which is equal to square root of 0.5 times 0.5 all over 24, 29, which comes out to be 0.01015. Okay, so let's use these two things that I'm circling here to fill out the bell curve. And that 0.01015, we'll just round it to 0.01. So in the center is the 50% win rate we expect to see if there is no such thing as a home field advantage. To either side, we would have 0.51, 0.49. We'll go out 2 here, why not? 0.52, it's easy after all. 0.48 with a standard deviation of 0.01. And the, let's see, was that given to you in the problem? Yeah, okay, now it's time to use this 54.96. That's the deviant statistic we want to test against, or use to build up evidence against the defendant, which is claiming to be 50% win rate regardless of home field advantage. So now we know that the defendant, or not the defendant, but our sample says that we actually have a win rate in 2003 over here of 0.5496. Awfully high, awfully high. And we're trying to build up the argument that P, the true population proportion of success, that is to say the true percentage of wins that you're going to have at home, is greater than 0.50. So we want to look for the probability that a sample, if the null hypothesis were true and you only had a 50% win rate, even if you have the home field advantage, quote unquote, would give you an outcome for the 2003 year this crazy. So we want to find the probability that you could have for 2003 this win rate right here for home teams, even if the null hypothesis were true. That's the way this courtroom case works. So we're going to say that blue stuff that I'm highlighting right here, that's the p-value, the probability value that we use to cement or to make the case against the defendant. The p-value is equal to the probability that p hat could be greater than or equal to 0.5496, which is equal to, didn't leave myself a lot of room for z-scores here. We'll do it right here. The z-score for this 0.5496 would be 0.5496 minus 0.50 all over the standard deviation of 0.01. Remember, I rounded. I ignored those last 3 digits. That z-score is pretty high, of 4.89. So the probability that a sample proportion would be greater than or equal to 54.96% win rate at home is equivalent to the probability that a data value on the bell curve would have a number of standard deviations greater than or equal to 4.89 from the mean, which is really, really tiny. 0.1, how many is it? 6 zeros? 3, 4, 5, 6, 5. Awfully small. Okay, so we have gone through, oh, and I forgot to label one thing. Not huge, but it would have been nice visually for you guys to see it. So we started with hypothesis here. That's sort of building out the courtroom case as it stands. Then we're trying to work towards the alternative hypothesis, what the defendant doesn't want us to conclude. We specify the model, and then right here we have, oh man, I really don't have much room to write this. Mechanics are everything starting here on. I'll put a line to separate the model part of the conversation from the mechanics. So the mechanics is basically all the math involving the bell curve. Okay, so we're done with the mechanics because we got a p-value. That's the big focus. We need to make sure that we get a p-value to accept the alternative hypothesis or fail to accept it. All right, so conclusion here. What can we conclude? Okay, so if H naught were true, that is to say, if the win rate at home for these baseball teams were just 50%, this sample proportion for the year 2003 equal to 0.5496 would occur fewer than 1 in 10,000 times with such a small p-value, with p-value equal to, we found it to be 1, 2, 3, 4, 5, 6, 5. Awfully tiny. Therefore, I reject the defendant's argument here that the win rate's 50% in favor of the alternative case that the defendant's guilty, i.e. that the true population proportion, the true win rate for teams when they have that home field advantage is indeed greater than 50%. That is to say that home field advantage is a real thing. All right, let me check the time here real quick to see where we're at. 17, okay. I think it's going to be advantageous because this whole process, even though, again, the math isn't truly new, the way we're using it totally is. Let's check out another that I've got set up. All right, example 2 here. A study from Punjab, India reports that in 1993 in one hospital, 56.9% of the 550 live births that year were boys. It's a medical fact that male babies are slightly more common than female babies. The study's authors report a baseline for this region of 51.7% male live births. Okay, so again, we need to think in terms of the defendant in the courtroom. That's the defendant. We're going to build up a case as to whether or not he's guilty or to see if we don't have enough information to conclude he is guilty. Could this deviation from the historical percentage of 51.7% be explained just from natural sampling variability? Or is this evidence to suggest that there really has been a change in the percentage of male births? Okay, so just like we saw last problem, we start with our hypotheses. The first is the baseline assumption. That's what the defendant is claiming to be true, H naught. Don't focus, I wouldn't care too much if I were you about where this capital H naught comes from. It's just old, I don't know, old terminology at this point. The defendant's claiming that even though we've got this sample in 1993 where we got a lot of male births, it doesn't matter. The true percentage of male births in this Punjab, India area is still 0.517. Well, we are testing against that, the alternative hypothesis, that the true population proportion of male births is not equal to. Notice the difference here. Last slide we wanted to see if home field advantage was a thing. We wanted to see if the percent of the time that you're going to win when you're at home is greater than 50. That's a home field advantage. Obviously, a home field disadvantage would be that P would be less than 50%. Here we're checking to see if there is any deviation at all from this 51.7% baseline male birth rate that we know to exist in Punjab. Okay, so those are the hypotheses. Onto the model. This will look pretty much identical to what we saw last slide. We're using the same bell curve in the exact same way. Randomization. I must assume the 550 births are a representative sample. Have to assume that. I can't know that. Have to assume that to make a conclusion here. 10% condition. The 550 births in my sample are less than 10% of all births in Punjab. And last but not least, success failure, just like we had last slide. Success failure. That again in P naught standing for the population proportion that the defendant's claiming to be true is equal to 550, or sample size, times 0.517. That is indeed greater than 10. And Q naught would be 550 times 0.483, also indeed greater than 10. Okay, cool. So we are a go on the normal bell curve. And again, the model that I told you that would be sticking all throughout Chapter 20 is the same. It's the one proportion z-test. It's the tool that allows us to make a case against the defendant, the p-value of 0.517. All right, so we have hypotheses, the model. Now to the mechanics that I meant to label last slide. We have this so far. We know that we're trying to build a bell curve here. And on that bell curve, obviously, we need a mean. The mean, the expected value of a sample proportion, we're going to assume the defendant to be innocent. We're going to assume that 0.517 to be true, and then work against that assumption as best we can. The 0.517 is the expected value. Standard deviation using the p naught q naught over n. I'm going to take a little bit of a shortcut here and not write that out. All over. So this is the square root of 0.517 times 0.483, I believe that is, over 550. Comes out to be 0.0213. So there's standard deviation. And p hat, the sample proportion we're working with, is 0.569. So let's fill this out on the bell curve. We have 0.517 here. To the right and to the left, we're looking at 0.538 and 0.496. This is the distribution of sample proportions. Okay. Now, we need a z-score. Let's do this in blue. Let's start to talk about the actual sample we've got to work with in a different color here. So 56.9% of these 550 births were male. That's awfully high. So the z-score we're working with off to the right side here is equal to 0.569 minus 0.517 all over 0.0213. That comes out to be 2.44. So way off to the side here, we've got the z-score of 2.44. Now, think about what the alternative hypothesis was that we were building up a case for, against the baseline assumption, against the defendant being innocent, null hypothesis. That was to say that P naught would be not equal to 0.517. So instead of looking just at how exceptional are we off here to the right, if we want to check to see if this could be true, or if it could not be true, we also care about, this is called a two-tailed test. Whenever your alternative hypothesis has this does not equals, you're using a two-tailed test here. On the other side, we care about the likelihood that we would have a really low value with that same z-score of 2.44. Negative this time because it's below the mean. So we're looking to see how exceptional is this value, but also if it were on the other side of the mean, how exceptional would it be there too? So everything highlighted in blue here, all of this stuff will give us the p-value. So let me write this out. We've got, don't want to lose my place. The p-value this time is equal to twice the probability that our z-score would be greater than 2.44. Because again, the bell curve is symmetric, so you've got this probability to the left and to the right. Find simply the probability to the right over here, double it, and that's everything in blue that's shaded. Equals 0.0146 using normal CDF. So conclusion time. Last piece of the hypothesis testing procedure. With such a small p-value, and I guess I'm interchangeably going from capital to lowercase, no big deal there, whichever you want. I reject H naught. That's the defendant's argument that the true percentage of male births in the region is still 51.7%. Oop, I don't need a comma. In favor of the alternative hypothesis that 51.7% male births in Punjab, India is now no longer the case. All right, I'm tired. You're probably tired. I don't have enough time tonight to get the the last unit tests posted to the grade book, but I'll do that as soon as I can this week. I will submit this video now, and in the morning you will see the notes on my big campus to follow along with this. Good job on this video, guys, and I'll see you next time.